Lesson 212. Today, we're going to look at manipulating log functions, which means we're going to take a log function and change it to where it looks different, but mathematically it's the same. Before I start this lesson, on your first slide, where you have some extra space, what I want to do is a quick review, and I want you to write down some things that are very important. So this is a review, and I believe it's a review from lesson 2.4. I think it's lesson 2.4. But either way, what I'm reviewing here is how we manipulate exponential functions. So as a start, for exponential functions, I'm just going to use a base of 2. The base can be anything. I'm going to say the base is 2. If you were manipulating any value raised to the power of x, the thing I wanted to get across on this day is the definition of an exponential. Every table for an exponential looks like this, that if the x values are adding, what's happening to the y values? They're multiplying. And if the x values were subtracting, that would mean the y values are dividing. We had 3 properties, 2 extra rules that came with it. The properties I want to review here on this slide were these. The first one was called the product property. The product property. So I'm going to stick with the base of 2 because that's what I wrote up there. 2 is irrelevant. You can make it a 10, you can make it a 20, you can make it an e, you can make it a pi. Doesn't matter. I chose a 2 up here, so I'm going to use a 2 here. The product property says this, and if you have 2 raised to the power of, let's just say it's x plus 3. You could rewrite this. Now tell me, what's right now adding? Is that the x's, the inputs, or the outputs, the y's? The inputs. The x, the inputs, they're adding. If x's are adding, that's the same thing as multiplying your y's. And the way I wrote up here, y represents 2 to some power. So what does that mean? We could rewrite this as 2 to some power, that power being x, times the y's are multiplying. 2 to the x times another 2. But this time, it would be 2 to the x times 2 cubed using the example I have there. That was the product property. X's adding became y's multiplying. Y represents the whole equation. There was a quotient property. You remember that one? Do you remember what the quotient property was? Divide. So divide would be the y column. So what's going to be happening in the x column? Subtract. So let's just change this. So almost the same equation, but instead of 2x plus 3, how about 2 to the power of x minus 3? 2 to the power of x minus 3, that's x is subtracting, would be the equivalent of the y's. Again, y represents the entire equation. So the positive value of x goes to the numerator, 2 to the power of x. The negative 3 goes to the denominator, which, by the way, is one of the 2 rules. If you remember a negative power, you can take the reciprocal of it. And so since that minus 3 is negative, it goes, I put a minus 3 there. I shouldn't have done that. Someone correct me. I made a mistake. It's a positive 3 once it goes to the denominator. Okay, we had one more property. It was called the power property. We also had one more rule, the other rule. So the one rule was negative power, so I just walked through right there. The other rule is if it was a fraction, and that's where you could turn into a root as well. But I'm not going to go over that today because that doesn't matter for us today. Power property said this. If you have a base raised to a power, and that power happens to be multiplying, I'm going to say 3x this time. Before I tell you what the answer is, let's look at the rules. What's the 3 doing to the x this time? Multiplying. Is that on there? Do you remember what I said? If your x is breaking the rule, how we change the problem? Very good. If you break the rule. So is that one of the rules there? No, multiply is not supposed to be there. If you're breaking the rule here, what you're doing is you're changing your y. You're changing your base. Breaking the rule over here changes the base. So the base is not going to stay as a 2. Basically what happens is this. I'm going to put a parenthesis right in there. You basically do that number. You change your base. What is 2 cubed? 8. It becomes 8 to the power of x. The power property stated this, that a power raised to another power, basically, actually, let me write it the way they say it here. They say 2 to the power of 3x is equal to 2 cubed raised to the power of x. That's actually how we wrote it in the notes. That if the x's are multiplying, you can do it as a power raised to another power. And I just skipped that step. I put a parentheses there. What is 2 cubed? 8. So truthfully, I should have wrote that first, then put 8 to the x after. I'll fix it. That was the power property. Right there. Sorry. With that, we're going to start a new lesson. I wanted to review you on your exponential rules. So you all have the exponential rules down now? Those 3 rules? Okay. Today, we're dealing with logarithms. They are the inverse of exponentials. So if exponentials had 3 properties, how many properties do you think logarithms are going to have? Looking around the room, I see a few people doing like question marks with their face as they put up a 3. The answer is 3. We're going to have 3 properties today. Here they are. Your second slide says you have 3 properties of logarithms: the product, the quotient, and the power. Here's the only difference. Go down at the bottom if you have space. Right here at the very bottom, here's what I want you to do in the form of a table. I want you to do this. Put your x here, and then put y equals log x. It doesn't matter what the base is. Just write that down there. What's the rule with a logarithm? It's not x is add or subtract, y is multiply, divide. What's the rule for a logarithm? X is multiply, y is add, or x is my divide, and in that case, y's will subtract. From there, you can get your properties. That, oh my goodness, what's going on with my board? Okay, here, think of x as like the input, the inside. Here, what's going on in the inside, the input? Multiplying. If that's the x's multiplying, what does that mean? The outside, the y's, the logs are going to be doing? They're adding. Y represents a log, the logs are adding. Okay, here, what's happening on the inside? X's are dividing. What does that mean is going to happen with the logs? They're going to subtract. Finally, we have a power property. We said over here, I didn't write it down, I should have. The power property, that changed the base. You remember that? Change of base. What's weird on this one is the change of base we're actually going to do a little bit separate. This isn't going to necessarily change the base here, but we do have a change of base that's coming later. We're going to have a power property, but we will also change the base in another section, okay? So there's your properties. You can look there. We'll explain them as we go. But let's get started. Example 1. What it says to do is each one of these I have given you multiple logarithms. We want to come up with something that's equivalent. That means equal to, but written as one single logarithm. So right now, on example 1a, how many logarithms are there? 2. We want to write this as 1 log. So here's the steps necessary. To write this as 1 log, the first thing you must do is I'm going to call it, make it one clean, all right, make each log a clean log, meaning no numbers out front. This one has a number 3 out front. One of those 3 properties, specifically it's the power property, says if there is a coefficient multiplying the log out front, you can make that a power on the x. This is called the power property. If you want to look back, this was called the power property. The power property states that if you have a number multiplying the log, that's like breaking the rules. Let me go back here one more time. Right now I have a 3 multiplying the log. Are the y's supposed to be multiplied? No. So what I do is I don't change the x's by adding, subtracting like that. You just make it a power. According to the power property, this becomes log base 4 of x cubed. Today you'll notice anytime it's more than one term, I'm going to put a parenthesis. If it stays as one term, I'll leave it without a parenthesis. So I want to put a parenthesis around x cubed because now it's not just a value of x, factor of x, it's now x cubed. So I'm going to put a parenthesis around it. Plus log base 4 of y. Notice no parentheses. You're not wrong if you put a parenthesis there. You're not wrong if you don't put a parenthesis here. I do it this way because that's what AP Classroom does. I'm just modeling how their answer will, what they do. That's the power property. So I made these 2 clean logarithms. What do I mean by clean logarithms? It means it's not a 3 log anymore. It's just a log and another log. So here's my question for you. What's happening with these 2 logs? They're adding. The log represents the y's. If y's are adding with the logarithm, that's the same thing as doing what? X is multiplying. That's called the product property. What you just stated is called the product property. When y's add, meaning logarithms add, that's the same thing as the x's multiplying. Since I have this as 2 individual clean logarithms, you just write log base 4. It's a clean log, but this time they multiply. Since there's more than one factor, I'm going to put it in parentheses. X cubed times y. And that would be your answer right there. So in case you missed it on the previous slide, when you're dealing with logs, and it doesn't matter what the base is, if you're dealing with logs, the x's are supposed to multiply or divide, the y's add or subtract. Because these 2 logs were adding, the y values were adding, we changed it to an xi, the inside multiplying. This one was that rule breaker where it doesn't go off of there. And so what it does is it just makes a power. Okay, let's try it. Let's go to the next one. I have 3 logs this time. I want to combine it into 1 log. What's your first step to combine those into 1 log? I heard the name, power property, but visually, can I combine them right now? No, why not? Are they clean logs? Which one's not a clean log? This 2. We're going to do the power property on that 2. That 2 is going to become a power of z. Sorry, let me write it down. Power property. How about that? Power property. So I have log base 3 of 5 minus log base 3 of x minus log base 3, and I'm going to use a parenthesis. Why am I using a parenthesis? Z squared. I put a line on my z's just because my z will look just like a 2. Now, as you look through there, Brianellis, do I have 3 clean logarithms? Okay, so if you have 3 clean logarithms, what can I do with them now? Combine them. Right now, these logs are subtracting. What can you do with logs that are subtracting? Divide the inside, divide the inputs. So that's called the quotient property. That's the name of this one, is the quotient property. What you do is this: 3 clean logarithms, all either adding and subtracting. You make it 1 clean logarithm. But if there's subtraction involved, it's going to end up being a quotient. So we do a parentheses with a division. Again, you don't have to do the parentheses, but College Board will, so I will. Anytime it's more than 1 factor inside a logarithm. I want you to take a guess. I know you've never seen this before, but you take a guess. What do you think goes to the numerator? I heard the number 3. 3 is not it. 5 is it. 5 goes to the numerator. Now, why do you think it's 5? Is it because the 5 is first? Answer, no. There's a different reason 5 went to the numerator. What's different about this log than these two? Oh, that's true. 5 is a number, but that's not the reason why. It's because this log is positive. What can you tell me about these two logs? Negative. Negative logs go to the denominator always. So even if I did x times z squared, doesn't matter. What matters is if it's a negative log, it goes to the denominator. If it's a positive log, it goes to the numerator. You can separate them with multiplication symbols. That doesn't matter. It all matters about its location. Numerator is a positive log. Denominator is originating from a negative log. That right there is your answer. Okay, now I think it's still a little too early to give you a practice just because I want to make sure you see the three rules, feel real comfortable with them. So this on the very first example, I have a part C and D we're going to look at now. Okay, let's look at example C. I have 3 different logarithms. Leslie, what do you think? Would you say these are 3 clean logarithms? No, very good. What's wrong or what's not clean about them? There's a coefficient of 3 and a coefficient of 5. What can we do with coefficients? That means multiplying. But multiplying the y's. It's the power property. Again, the rule breaker is the power property. This is the rule breaker for both situations. It's, oh, my slider quit working all of a sudden. The power property is the rule breaker for both logarithms and exponentials. The power property is the one that kind of breaks the rule, if you will. So here, what you do with the power property is that means you're multiplying your y's, which is not what you're supposed to do with a log. What you do with that is you don't add the x's. What you do is because you're breaking a rule. Y's aren't supposed to be multiplying, but they are here. Instead, what you do is you make your number get a power. So this is called the power property. So we should end up with log base 2 of x cubed, and I'm putting that in parentheses because it's not just one term, minus log base 2 of y plus log base 2 of z to the 5th power. All right, Dami, what do you think? Clean logs, not clean logs? Clean. What can I do with them? 3 individual clean logs. Yeah, this one, there is a product. That's this log and the positive log. If you have your addition of logs, it's a product property. What can I do with the negative log? Quotient. We can do quotient and product. I'm going to do them in one step. We're going to do, whoops, I forgot my U. The quotient and the product property here in the same step. Three clean logarithms, that's going to be a log with a base of 2. Since quotient is involved, there will be a division. So what goes to the numerator here? X cubed. And z to the power of 5. That's because this is a positive log. Notice it's not going to multiply with y just because they're back to back. Honestly, the order does not matter with logarithms. What does matter, if it's a positive log, it needs to go to the numerator. If it's a negative log, the value needs to go to the denominator. The answer here, that right there is our answer. X cubed times z to the 5th over y. Log base 2 of x cubed times z to the 5th, all divided by y. There's your answer right there. All right, we're going to do this one more time. Jessica, you want to start us off? What do I do with the 2, the 5, and the 3? That's right. They become, respectively, the powers of A, B, and C. Good. What property is this going to be called? This is the power property. According to the I didn't ask you, what does ln mean? Let me see that. Natural log, or a log natural. It means it's a log with a base of, not 10, that's a common log. That would just be if it just said log. Log natural is a log with a base of e. You got it. Log with the base of e. So I have the natural log natural of a squared plus the log natural of b to the power of 5. Finally, a subtracting natural log natural of c cubed. All right, Isabella, what do I do with 2 logs that are adding? They're going to be multiplying on the inside, so that's a product property. Good. What about a log that's subtracting? Divide. That'll be a quotient property. So we're going to do a product property, and we're going to do a quotient property. So 3 clean natural logarithms. The natural log, that means a log with the base of e. Any log that starts or that originates as a positive log goes to the numerator, which in this case is a squared times b to the power of 5. Good. And in the denominator, c cubed. You got it. And that would be your answer there. All right. I think y'all are now thoroughly ready to do your first DOL. If you go to the back of the packet, I want you to attempt number 3. Number 3 in the back of the packet. All right, now to example 2. This time, they're giving us 1 log, and it says write an equivalent expression. That means something that's equal by expanding the logarithm. Okay, so this time, we are still using the same setup we've been using, meaning that with a logarithm, what makes a logarithm is that the x's are doing something, the logs are doing something else. When x's are multiplying, what are the y's doing? Adding. And when the x's are dividing, the y's are subtracting. That's what makes a logarithm a logarithm. X's are geometric, whereas y's are arithmetic. That was your relationship. Let me put the x in the middle there. Okay, so now when you look at this 1 logarithm, what's happening inside this 1 logarithm? Dividing. On the inside is the x. The input is dividing. So if the input is dividing, that's the same thing as making the output subtract. So what I'm going to do first here is, what's the name for dividing? Another name for that? Quotient. We're going to do the quotient property first. I can do this because it's a clean log. You can do product and quotient when you have a clean log. Whoops, I'm writing property. That's what I mean. Property. There we go. Quotient property states that if you have a log where the inside, the input, the x values are dividing, you can make that become where the y's are subtracting one another. So I'm going to rewrite this as log base 3 of x squared. And I'm putting x squared in parentheses because it still is not just one factor, but it's x times x, or x squared. So I'll put in parentheses. The denominator becomes a negative log minus log 3y. Now the y doesn't need to be in a parenthesis. I mean, you can put a parenthesis there, but AP Classroom won't if it's a single value, so I won't either. So that's the quotient property. All right, question for you. Are we totally expanded? No. What can I do to expand this further? I can do something with the power of 2, the square. What can I do with the square on logs? You can perform a power property and move it where it's multiplying the y values. The power property is where you basically break a rule. What am I saying? Are the y's supposed to be multiplying? No. So what I'm going to do here is power properties, when you break that rule, this 2 is going to multiply the log. You might notice I did not put a parenthesis around the x. That's because that term is now just an x. I'm going to leave it like that. That right there would be your answer. That's fully expanded. Say it again. The power property for both exponentials and for logarithms is where you don't actually follow that rules. That's where the whichever, if you're talking exponentials or logarithms, whichever values, inputs, outputs that are supposed to be adding and subtracting, that's when you multiply in that column. Instead of solving the problem as normal, what happens is you break the rule and do something a little different. So in this case, for logarithms, you move the power to the front. It's a coefficient. All right, let's try the next one. This looks like an IN. It's not actually IN. What 2 letters are those? LN. And what does LN stand for? A log natural or a natural log. A log with a base of E. That's right. Okay. I have one natural log. It's all alone. It's a clean log. But on the inside, I have all kinds of stuff going on. I can take this one natural log and rewrite it as how many different logarithms? 6. Very good. We're going to rewrite this as 6 logarithms. I'm going to use both the product. This is going to be the product and the quotient property. So the quotient will make the denominator negative, but the product is technically when you make the numerator all individual positive natural logs. So I'm going to have the natural log of a cubed. I'm going to need more space than that, I know it. I'm going to scoot that over. I'm going to have the natural log of a cubed. Now that b is multiplying on the inside, so with multiplication comes multiplying the inside means we add on the outside. So plus the natural log of b plus the natural log of c cubed, good, plus, here, see a few heads shaking no, not plus now, minus, because we're now in the denominator, minus x, natural log x. Now listen, they could try to get tricky and put a dot there. That makes no difference. It's all about location. What's the y truthfully doing within the natural log? Is y technically multiplying within the natural log, or is y dividing? Dividing. For that reason, it's a negative natural log of y. And finally, and I'll put z squared in parentheses because it's more than one factor. Are we done with the problem? No, what can we still do? The power property. So I'm going to take all my powers and make them multiplying coefficients. So now it becomes 3 natural logs of a. I'm going to drop the parentheses because a is its own factor now. Plus the natural log of b. Plus 3 natural logs of c. Minus the natural log of x. Minus the natural log of y. Minus 2 natural logs of z. There's your answer right there. Questions over that? Well, if not, I think you're ready for your second DOL. How about number 6? Go try number 6 now. All right, now let's take a look at example 3. It says here the function f of x is equal to log 6 of 6x is a horizontal dilation of the function g of x equals log 6x. Show that function f can also be written as a vertical translation of g, function g, with f of x equaling g of x plus k, where k is constant. Okay, here's what I want you to gather here. Our answer should look in this form when we're all done. Our answer should be in this form, where k is a constant. What does a constant mean? By itself? Is that what we said? Okay, more specifically, k is a constant. It means more than just by itself. K is, what are things that are constant that never change? A variable is something that changes. Constant is something that does not change. What's an example of a variable? Someone say x. X is a variable. What is an example of a constant? Someone say 2. 2. Why is 2 constant? Because 2 is always 2. 2 doesn't change. 2 is 2. Okay, this is the idea. Our function should look like this at the very end, which means if it's supposed to look like f of x equals g of x plus k, that means our answer is going to look like, what is f of x the same thing as? Log 6 of 6x is going to equal, what's g of x according to the problem? Log 6x. And then we're going to have some number after it, plus or minus some number, because a constant can be a negative number as well. So plus or minus some blank number. That's what our answer is going to look like at the very end. Does that make sense? Let's get there. What I would suggest you do when you're solving these type of problems is start with the more complex of the two. I think it's always easier to start with the more complex and to simplify rather than to start with the simplify and complex it. That just doesn't even sound right. So which one's more complex? Let's start with log 6 of 6x. We're going to start with the more complex side. And what we're going to do is the same properties we've been doing, but we're going to get our answer in this form. So what property do you realize we could perform here? By the way, we're starting with the more complex, which we're saying is f of x. We're starting with f of x. What property can we do? That 6 is multiplying. I'm multiplying an x. If you're multiplying an x on a logarithm, that's the same thing as, it's the product property. Multiplying an x is the same thing as adding a y. We're going to do the product property. So if we're doing the product property, that means that multiplying x is going to become what on the y? A multiplying x becomes a adding on the y. The y is represented by the log, so it'll be log 6 of 6 plus log 6 of x. Now what could I do? No, I don't have any powers. Can't do a power property. I can do something else though. From lesson 2.9. This is lesson 2.12. 4 classes ago, when we first taught you logs, I taught you what you can do with log 6.6. They simplify. You can evaluate that. What is log 6 of 6? 1. So after evaluating, I'll just write evaluate. Evaluate just means basically you did the math. For example, 5 plus 3. Evaluate that for me. What's 5 plus 3? 8. I would not say solve if I'm being a true using mathematical language. Solve means you're solving for a letter. If I just said, what's 5 plus 3? That's an evaluation question. The same thing. What's log 6 of 6? 1. So I have 1 plus log 6x. Okay, notice what we had. We started with f of x, the most complex. What is g of x represented by? Okay, so we said f of x and all these things were equal. This f of x is equal to this down here with this is g of x. What must this 1 be then? That's your k value. Therefore, log 6 of 6x is equal to log 6x plus 1. That right there would be your answer. Now, to make our connection, to make sure we fully understand the connection from earlier, I've been writing down that if x, and you're looking at a table of log with an x and a y, with x and y equals log x, we would say that x is either multiply, and if x is multiply, what happens to the y? They add, or x is divide, and that means y's will subtract. Okay, what they also mentioned in this problem is they use transformation language. Transformations we learned on lesson 1-12. What we learned on 1-12 is if that you are multiplying or dividing, you can call this a dilation. Remember, there were 3 types of transformations. There's reflections, dilations, and translations. Do you remember that? So dilation was when you multiply or divide. Do you remember what you call it when you add or subtract? A translation. Very good. A reflection, by the way, is a negative, if you have a negative. Finally, we had a different word for x. It was either horizontal or vertical. Which one meant x? Horizontal. And if it's a y, it's not horizontal, it's actually... Okay, now why do I write this? This is just showing you different language from lesson 1-12. What I could say here to complete the instructions is, on this problem, the 6 is multiplying the x. That means if it's multiplying on the inside, is it horizontal or vertical? If you're dealing with the inside, you're dealing with a horizontal. This is a horizontal, and you're multiplying. When you multiply, that's a dilation. I'm going to put it next to it. This is a horizontal dilation. Over here, what's happening? I'm adding 1. Am I adding 1 on the inside with x? No, there's no parentheses there. So am I adding 1 on the inside? I'm adding 1 on the outside. If it's on the outside, is it vertical or horizontal? This would be vertical. And when you add, the word is translation. What this is showing you, and what the instructions are saying, is that on a logarithm, a horizontal dilation could be played out to become a vertical translation, or vice versa. A vertical translation could be played out to be shown to be a horizontal dilation. They can be one and the same. That's because when x's multiply, y's add. That's why a horizontal dilation could become a vertical translation. I don't know if that makes sense or not, but that's what this is trying to say. That's what the explanation up there is. Okay, because that's kind of weird, I'm going to do another one. I'm not just going to do one this time. I'll let you see it a second time. So this one says, show that f of x equals log 2 of 8x squared can also be written as transformations of g of x, where g of x equals log 2 of x. This, if it were a true question, they would have some type of equation like that. So I'm going to add it right here. So I'm going to add that right here. Let's go add this to your instructions. How about show that f of x equals a times g of x plus b. That's what I want to prove on this one. I'm just adding this. You might be going, where'd that come from? Well, it's coming from my brain because I know what the answer is going to be. Okay, so where do I start? The simple or the complex? Let's start with the complex, which in this case is the equation f of x. Log base 2 of 8x squared. Now again, that's f of x. I'm just going to put that there so we have it for later on. So we're starting with f of x. All right, what could I do to make this complex a little simpler? There's 2 different properties we might be able to do. What are the 2 things you see? The power and the product. Okay, here's my question for you. It's about order. If I did the power now, that would be saying the 2 belongs as a power of both 8 and x. If I do the product first, that would be saying 2 is not a power of 8, and so I need to separate them before I do the power. What is the truth? Does this square affect the 8, or does it only affect the x? Does that 2, the square, affect the 8 here? No. So we're going to do the product property first. We're going to first do the product property. So what can I do when x's add? I'm sorry, I said that wrong. When x's are multiplying. What can I do when the x's are multiplying? Y's add. So we're going to make this log base 2 of 8 plus log base 2 of x squared. Okay, a moment ago you said there was a second property. What's the other property now we can perform? Power property. So let's now do the power property. What can you do? The power property is one that doesn't seem to follow the rules. It's just kind of its own thing. What can you do with the power property? Not cancel. It moves to the front of the logarithm. So it's going to be log base 2 of 8 plus 2 log 2 of x. I can do one more thing. What else could I do on this problem? These don't cancel. That's a great thought to cancel that out. That doesn't work though. You can cancel when it's log 2, 2. That's when you can cancel because ultimately you're evaluating. The answer is I can evaluate, but it's not this log. I can evaluate over here. What's the purpose of a log? It finds the power from the base. It finds the power from the base to the number. What's the power required to get a 2 to become an 8? 3. 2 cubed is 8. The answer there is 3. We can evaluate and say this is 3 plus 2 log 2 times log base 2 of x. Now, remember what we were supposed to show early on? We were supposed to show that f of x is equal to this. I started with f of x. That means all of this down there represents these pieces. Okay, let's start with the easiest. They told us what g of x is. What is g of x? Log 2x. Okay, come down here, log 2x. That's our g of x. Okay, up here, a is supposed to multiply with g of x. What's multiplying with g of x? That's our a. B was supposed to add to the g of x. What value is adding? That's our b. So we could rewrite this as f of x being log base 2 of 8x squared equals a. What did we say a is? 2 times g of x is log 2x plus b, which is 3. There's our answer. Does that make sense? As far as transformations are concerned, because this problem does mention the word transformations, as far as transformations are concerned, the squared up here, I don't know how to name that as a transformation, so I'm going to start just with the 8. Is that 8 on the inside, meaning horizontal, or is it on the outside, being vertical? It is on the inside. So what word should we use? Horizontal. It's multiplying. What word means multiply? Reflect, dilate, or translate? Okay, that's a horizontal dilation. And technically you would say by factor. Are your x's liars or truth tellers? Liars. So you don't actually multiply by 8. You divide by 8, so you'd say it's 1 over 8. Now that horizontal dilation by factor 1/8, that corresponded to this 3 over here. That's what produced that 3. The squared produced the 2. That produced this 3. So what is this 3 over here? Is this horizontal or is this vertical? That's vertical. When you add, is it a reflection, dilation, or a translation? That's a vertical translation. Not by factor, sorry, that factor means multiply. Which way would you go if it said plus 3 on the outside? Nope. Plus 3 is that would be if it was in parentheses. If it was in parentheses, now it would be left 3. It's not in parentheses, so it's up or down. Up 3 because y's are truth tellers. Up 3 units. That 2 right there, that came from this 2. I don't know how you would label that as a transformation, but I do know right here, this would be called, that was a rule breaker, remember? X is to a power is not part of the rules. This would be a horizontal or vertical. Is that inside the log or outside? That makes it vertical. When you multiply, dilation, and are the y's liars or truth tellers? Truth tellers, yeah. So the 2 in red corresponded to each other. The 1 in blue came from this squared, and I don't know what you would say that is as a transformation. I don't think it is a transformation. But the red follows the rules. X's multiply, y's add. That multiplying by 8 became an adding of 3. Okay. I walked through twice how you can transform equations and solve with them. I want you to try DOL number 4. Start with the most complex, work your way to the simple. All right, change of base property time. Now, on exponentials, I told you we had a change of base. Let me go all the way back here. We had a change of base on the power property for exponentials, but I told you for logarithms, the power property is the rule breaker, just like the power property was a rule breaker here. However, the change of base is not the power property for logs. A change of base is it's kind of like its own thing. So when I come here, here's how the change of base property works. Just like exponentials, there is a potential to change the base. I'm going to say it again. You can change your base. Here's how you change your base on a logarithm. I'm going to give you a bunch of examples. Just write them down in the white space, and you'll probably start to catch on pretty quick. So examples. On a logarithm, you can change your base anytime you want. That's what's different than exponentials. It's not just when it's the power property. Here's how you change your base. If you had log base 2 of 7, you can change the base. You can actually change the base anytime you want. But I'm going to change it on log base 2 of 7. Log base 2 of 7, what this is saying right here, you can change the base. If you change the base, what happens is you make your y's divide. So write log. I'm getting ahead of myself. Let me write this, then I'm going to come back over here. What it becomes is if you're going to change your base, notice here this says log with a base raised to an x is equal to log x over log base. This becomes log 7 over log 2. You could pick any base you want whatsoever. It doesn't matter the base. If I don't put a base at all, what does that mean the base is? 10. Right now I left it as common log. It's a base of 10. Okay, let me go back up. Sorry, I skipped something. Remind me on a logarithm. When we do a logarithm, what is the normal rules that we follow? What did the x's do? Multiply. If x's multiply, y's add. If x's divide, then guess what? Y's subtract. When you change a base, it's still breaking a rule. Change a base is breaking a rule. I started to say that and I realized, wait, I don't even have it up there. When you change your base, what am I actually dividing here? Am I dividing the x values or the y? Look, notice y is the log. What am I dividing? I'm dividing y's. Are my y's supposed to divide? No. So when you break a rule, if you have divide here, which you're not supposed to do, if you're breaking the rule, you can change your base. You change your base by breaking the rule, meaning you divide your y's. Okay, let me give you another example. Let's call it example 1a. Here's example 1b. Log base 2, 7. You might be going, Mr. Voorhees losing his mind. He just wrote that down. No, I'm not losing my mind. Log base 2 of 7 is the same thing as the natural log of 7 divided by the natural log of 2. Now, did I write the same two things here and here? No. What was the base this time? 10. What's the base here? E. Different base, but I'm telling you, mathematically, they are the same thing. So, does it matter what the base is? No. Let's do one more. How about example 1b? Log base 2 of 7. That's equal to, what's y'all's favorite number between 10 and 20? Here, 15. That's the same thing as log 15, base 15 of 7 divided by log 15 of 2. What do you think I'm trying to show you here? What do you think I'm trying to get your attention? That these two values, the 2 and the 7, are become the dividing values, but does the base matter? No. So if I wanted to, I could have just written this out as one log and just kept writing it over and over. Log 7 over log 2, which is equal to natural log of 7 over the natural log of 2. Can I change my base as many times as I want? You bet. You can keep changing your base. You can change it to whatever you want. All that matters is that the original base is the denominator, the dividing log, and the original number is the log in the numerator. That's all that matters. You could keep coming up with as many as you want. Here's one. I'm going to do a 2. That looks like a 12. Let me rewrite this one more time. You could do log 2, 7 over log 2, 2. And you might be thinking, why would he do that? Well, what's log 2, 2? And so that means we're right back to where we started with log 2, 7 over 1. Do you need to put log 2, 7 over 1? That's my point. Is you can change the base anytime you want to. It doesn't matter how many times you do it. However you do it, you can change your base if you want to. But to change your base, just like exponentials, you have to break the rule. So the rule is you divide your logs. That's what you're breaking. Okay, with that, come over here and try number 1 on the back of your packet. Try number 1. You want to see that again? There you go. All right, I want you to try number 1 on the back of your packet now. All right, example 4. We're going to go look at one more time. It says here, let f of x equals log base 3 of x and g of x equals log 9 of x. Show that f is a vertical dilation of function g by finding the value of k so that f of x equals k times g of the x. Okay, let me make sure you're following this. All right, at the very end, we should have our answer in this form. What represents f of x? We should have that log base 3 of x equals some value k times what's g of x. Okay, that's what we should end up with in the very end. That's what we should end up with, okay? We know where we're going. That's where we're going, except we're going to have some number to plug in for k. I suggest you start with the more complex side. Now, these look basically the same. Which one would you guess is more complex? The smaller number or the larger number? I go larger number. Let's start with log 9x. So I'm going to start with log 9x. x, which happens to be g of x. Go ahead and make a note there. That's g of x. We're starting with g of x. Okay, we need to change log 9x to try to make it more simple like this version. So what do I need to change? To make this more like that. Is there like a number in front of the log I need to change? No. Is there any like quotient or product? No. What do I need to change to make this like more like that? The base. We need to change the base. So how do you change the base? How do we change the base? Changing the base means you break the rule. Remember, x's on a log. What do x's always do? X's either multiply or divide, which means the logs either add or subtract. To break the rule, subtract. To break the rule, that would mean the y's are either multiplying or dividing. To change the base with the log, which one do you choose? Log that is dividing. We're going to break the rule by making logs divide. So come over here, change the base. This is going to be log divided by another log dividing. That's because we are dividing logs. That's what we're going to do. Log divided by another log. What are we going to put in the numerator? Come on, stay with me. X. What do I put in the denominator? 9. Perfect. We're changing the base. Right now I have a base of 10 because I didn't write one at all. What should I choose in regard to this problem? What base would I like it to become? A 3. Let's put a 3 and a 3. Okay, now what should we do? What can we do here? Do what now? Find the power. You want to evaluate. Let's evaluate that. We can evaluate log 3, 9. Log base 3 of 9. We can evaluate that. Remember, a purpose of a log is to calculate how many powers does it take to get from this base to this number. How many powers does it take? 2. I agree. So we're evaluating is what we're doing. Evaluate. When I evaluate, I have log base 3 of x over 2. Now, I have no better way of explaining that we got to our answer. We just don't know it yet, other than to point it out to you. I don't know how else to say, like, hey, you've gotten there. What is f of x represented by? Log 3x. That's what I have right here. And this was g of x. So what we could say here, I started with log 9x, which was g of x. I started here with g of x, and it equals f of x, which is log 3x over 2. Now, how I know that's my answer is, but I need to get f of x isolated. I need to get the f of x all by itself. So how do I get the f of x all by itself? How do I get f of x right here all by itself? Multiply by 2. That right there represents the answer. So this has to be the value k. This is the value of g of x. And this is the value of f of x. Now, I don't know how to say clearly, like, hey, we had our answer right there. But we did. Log 3x has to equal, not k. What do we just find out k is? 2 times log 9 of x. That's our answer right there. It says, show that f is a vertical dilation of g. I think I have that backwards. That g, f is a vertical dilation of g. Well, I don't know. Let's just write it out. This right here, what am I multiplying, x's or y's? I'm multiplying the y's. Does that mean it's vertical or horizontal? That is a vertical. When you multiply, is that a reflection, dilation, or translation? It's a vertical dilation. Let me put that right now, space. Vertical dilation by factor. Is the verticals liars or truth tellers? Truth tellers. by factor of 2, by factor 2. That right there would represent the answer. We have it written in the same form. All right, and with that, we have another one for you to try. Go try number 2 in the back of your packet. All right, example 5. Let's put it together. Everything from lesson 2.9 through 2.12. All right, looking at this problem here, it says, what expression would be equivalent to all of this? Well, question for you. Let's see if you caught what you were supposed to learn today. Can I combine all these logs together all right now? Why not? Not good old clean logs. What should we do first then to clean it up? Power property. Let's make this 2 become a power there. This 3 becomes a power here. This 5 becomes a power on the y. So we're doing the power property. Again, this is a rule breaker, which means we had multiplying y's, so it's not necessarily changing the x's. When I do this, I'm going to reorder this. You're allowed to reorder. I'm going to reorder it. I have log base 16 of 2 squared. I am not going to write this next log, nor this one. I'm going to write the last log. Why do you think I'm writing the last log second? Same base. Very good. Just make sure the last base was a log. The last log was positive, so make sure it's positive. Now I'm going to write the second log, log x cubed. This one doesn't have a base. What does it mean if you don't see a base? 10. Very good. Minus, let me put parentheses there. Minus log, parentheses y to the 5th. Again, common log, base is 5. Okay, now that I did that, what can we now do? I hear change base. I'm actually not going to change base. I'll show you why in a second. What can you do even before that, though? When you hear product property, the first 2 are the product property. That's correct. This is a product property. And then there's also a quotient property. This is log base 16 of 2 squared times 4. And this right here is a quotient property. So it's 1 log, but we make it divide. What goes to the numerator? X cubed, and the denominator? Y to the 5th. Good. Do y'all know what 2 squared times 4 is? 16. I'm going to evaluate this. That right there, 2 squared is 4. 4 times 4 is 16. We can evaluate this. What is log 16 of 16? That's going to become 1. It becomes 1 plus log x cubed over y to the 5th. That's why I did not change my base, is because I knew I was going to be able to evaluate. I would wait on changing your base and do that very last, because honestly, it doesn't get you very far in a lot of problems. But there it is. Your last problem to take a look at would be number 5. Submit those in once you complete number 5.